Hi, Hari Om to everyone. In this session, we are going to discuss Gauss's law and its application. I hope you have understand the Gauss's law in our previous video. Actually, Gauss's law will give me the definition or will give me the relation between the electric flux and also the electric field and also the area vector. And moreover, you would have understand when the electric flux or electric field will be greater when both electric field and the area vector will be parallel. That's the main point I am going to use here. And so this is the application of Gauss's law. What are the application I am going to find? The electric field. Our main aim is to measure the electric field. Electric field due to the first one is an infinite long straight charged wire. Okay, and a charged infinite plane sheet, two charged parallel infinite sheets, and charged sphere. Okay, these are the things we are going to discuss. Right. First, we will start with an infinite long charged wire. Look at the picture. In that picture, so this is an infinitely long charged wire. For my convenience, I have taken, it is made up of positive charge. It is filled with positive charge. Of course, we all know that for the positive charge, the lines will be radially outwards. It will be radially outward in all the direction. Okay, right. And next, we are introducing the term as some special term like the charge density. Linear charge density. What is a linear charge density? Linear charge density is nothing but here, suppose if I have taken any of the area, okay, in that area how the charges will be occupied. Yeah, we know that density is nothing but the charge, the mass per volume. Here I have taken, even it is being linear charge, okay, for the linear I have to consider the length. Suppose if it is a surface or the area, okay, I have to take surface. Suppose if it is a volume density. Okay, by the way, we are introducing the term linear charge density. Linear charge density lambda will be equal to Q by L. What is Q? The charge enclosed. What is L? The length of the conductor. That's it. Okay, and so the linear charge density lambda is equal to Q by L. And let us choose a cylindrical Gaussian surface of radius r and length L. Look at the picture. This is the picture. Okay, for this is a conductor. In this conductor, okay, I have chosen as imaginary cylindrical surface having the radius r, okay, and so look at, they have introduced some terms, some part, okay, like look at this part, this one and this one and this one. Okay, these three things are very, very important things. Okay, so the first one, this one will be placed in the cylindrical surface of the cylinder, and these two, okay, this one and this one will be a top and bottom layer of the cylinder. Okay, suppose if I have consider the cylinder, okay, so this is the cylinder. This is the cylinder. I can divide the cylinder into three parts. This is one and this is two, and the another one, this will be three. Okay, so now look at the second part, and what is the difference between second part and 1 and 3? Of course, 1 and 3 will be the same because both will be radially outward, this direction and this direction. But this surface will be acting radially in this direction. Okay, so that is the main assumption we are going to make. Okay, so the electric flux in this closed surface, is, okay, E dot dA according to Gauss's law. Okay, according to Gauss's law. So I will be considering, or I will be taking into three parts. That is the first part. This is the first part, and second part, and third part. What is the first part? It's a curved surface. What's the second part? It's a top surface. What is the third part? It's a bottom surface. Okay, and remember, in the cylindrical surface, it is the electric field vector and also the aerial vector will be parallel, and for the top and bottom it will be perpendicular. So that is the main point we must know. Okay, so for the curved surface, E is parallel to A, and the top and bottom it is perpendicular. So we will be having the electric field only at the curved surface, not at the top and bottom. Okay, so what happened at the top and bottom, the electric field will be zero, and the curved surface will be having some electric flux. Right. Now, so substituting this value in the equation of the Gauss's law, finally I will get phi is equal to q by epsilon naught. Right. Now, suppose if I substitute phi will be equal to q by epsilon naught and E into dA. Why? Because phi will also be equal to E into dA. What is dA? dA will be the area. What is the area for a conductor? It is a length. Okay, totally we are considering infinite long straight wire. So the total area will be equal to L. Okay, and here we are considering the width will be very small. That is why we are not considering L into B. Okay, so L Q lambda L by epsilon naught. Okay, by substituting the value E into 2 pi RL. Okay, look at the E into 2 pi RL, that is the area, E into dA, and the Q by epsilon, instead of Q by epsilon I am substituting lambda L. Okay, lambda L by epsilon naught. So finally E will be equal to lambda by 2 pi epsilon naught R. And look at the equation, this one, E is equal to lambda by 2 pi epsilon naught into R vector. So that is electric field is always acting perpendicular to the wire. Now, so the electric field due to infinite charge wires depend 1 by R rather than 1 by R square. Okay, but usually the electric field will be equal to E will be equal to Q by 4 pi epsilon naught R square, but for the infinite long straight wire E will be equal to lambda by 2 pi epsilon naught R. Remember, lambda is equal to Q by L. Right. The next one we are going to consider the charged plane sheet. For the charged plane sheet, look at the diagram. This is what the diagram we are going to consider, and that consider a plane sheet having the charge density, surface charge density sigma. I already told you lambda will indicate the linear charge density and sigma will indicate surface charge density. What is surface charge density? If lambda will be equal to Q by L means sigma will be equal to Q by A. Here we are having the length, here we are having the area. Okay, by the way, let P be the point R from the sheet. Look at the picture. So this is what the point P. Okay, these are the point P here, the two sides, because it's a plane sheet. For the plane sheet we are having one point here, one point there, left and right. Okay, right, and each side we are measuring the electric field. Before we are measuring the electric field, we are getting the electric flux according to the formula. Once again, we are having the same. Phi will be equal to E dot dA. Okay, and in the shape we are going to consider the cylindrical shape. Look at the cylindrical shape. For the cylindrical shape, the electric field and the area will be perpendicular. So in the cylindrical surface, in the curved surface, there won't be any electric field. But at the top and bottom, so the two parallel sides, and this side, okay, this side and this side, the electric field will be parallel. And this curved surface, there won't be any electric field. This curved surface, okay. So finally, the total electric field will be equal to Q by epsilon naught. What is Q here? Sigma into A. Okay. So the electric field is perpendicular to the area element at all the points on the curved surface and is parallel to the surface of the area. Okay. So the total electric flux will be equal to EdA into EdA. The two sides. Now the next is substituting the value. I will be getting since the magnitude of the electric field is this, equal to the surface is uniform. So E is taken out of the integration. So Q enclosed will be equal to 2 times of E into dA. Instead of dA, I am substituting lambda into A. The total area we are considering. Okay, instead of E, I am substituting E lambda by epsilon naught. Okay, so finally E will be equal to lambda by 2 epsilon naught. Okay, right. In the vector form, it can be written E will be equal to sigma by 2 epsilon naught into n, right? So from this we will come to know one thing, okay? So from the value of sigma, we can consider where the point P will be located, or where how the electric field will be located at the point P. So look at that. When sigma is greater than 0, P is radially outward. Okay. At the same time, when the sigma is less than 0, where at the point P will be, the electric field point is inward. So what is its meaning? When the sigma is greater than 0, it would be a positive charge. When the sigma is less than 0, it would be a negative charge. That is its meaning. Okay. The next we are going to discuss the electric field due to the two parallel charged infinite sheets. Okay. Look at the picture. So now we are giving two sheets. The one is this is, and for my convenient, I am just going to take two oppositely charged plane sheets. What may happen? You just think yourself. So this is a positive charge where the electric field will be radially outward. This is a negative charge. This will be radially inward, where the electric field will be radially inward. So when both will be acting radially inward, so what will happen? So look at this. Okay, look at this. So for the positive, it is radially outward. For the negative, it is radially inward. So what is happening at the between the plates? Look at the between the plates. Between the plates, both are pointing in the same direction. But in the case of outside, okay, look here. In the case of outside, both will be opposite direction. So what is obviously come to know? So there won't be any electric field outside the plates. So there will be an electric field in between the plates. So this is what the consideration, or this is what the assumption, or this is what the conclusion we are going to get to know. Okay. So the magnitude of the electric field due to an infinite charge plane sheet is, what is that? That is E is equal to sigma by epsilon naught. Sigma by epsilon naught. So it points perpendicularly outward. Yeah, of course, when sigma is greater than 0, and inward when sigma is less than 0. Okay, at the point P2, P3. Okay, look here. In the diagram, so look at the point P2 and P3. I already told you P2 and P3 will be located outside, so there won't be any electric field. So finally, the total electric field in between the plates, because each plate will contribute some electric field. That is, what is that electric field? In the previous session we have discussed, that is E is equal to sigma by epsilon, 2 epsilon naught. Okay, so sigma by 2 epsilon naught plus sigma by 2 epsilon naught, 1 by 2 plus 1 by 2 is equal to 1. So finally I will get sigma by epsilon naught. Okay, right. The next one. So here, what is the conclusion I will come to know? The direction of the electric field inside the plates is directed from positively charged plate to negatively charged plate. Yeah, it's obvious. Always the electric field starts from positive and terminates at negative. Okay, right. Next, the uniformly charged spherical shell. Okay, look at the diagram. In this diagram, we are going to discuss the two points, where when the point will be lies on the cylindrical surface, and the point will be lies or inside the cylindrical surface, and another one is point outside the cylindrical surface or the shell. Okay, so it is obvious that when the point is being outside the cell, the electric field will be radially outward. Okay, radially outward, and especially when the uniformly charged distribution, if you will be considering, the charge is uniformly distributed, so E dot dA will be equal to Q by epsilon naught. Okay, and so when I substitute, E will be a constant, so take it out from the integration, so E into dA, okay, which will be equal to Q by epsilon naught. And here there are the two things. Okay, the electric field must point radially outward when Q is positive, and radially inward when Q is negative. Okay, right. So when we choose the spherical Gaussian surface of the radius is chosen, okay, E and dA will be in the same direction. Okay, right. Now, so the finally, instead of dA, I am going to substitute 4 pi r square. What is a 4 pi r square? 4 pi r square is nothing but the area of a sphere. Okay, it's a shell. Shell is nothing but a sphere. Okay, so E into 4 pi r square is equal to Q by epsilon naught, and E into 4 pi r square is equal to, when I take Q by 4 pi epsilon naught r square, and R vector will give me the direction of the electric field. And so the electric field is radially outward when Q is positive, radially inward when Q is negative. And next one, when the point is on the surface of the cell, when R is equal to capital R, so there won't be any change. Or when R is equal to capital R, E vector will be equal to Q by 4 pi epsilon naught R square. Okay, when the R is inside the shell, when the point is inside the cell, what is happening? Okay, so here when I apply the Gauss's law, Q by epsilon naught, inside the Gaussian surface, okay, there won't be any charge. Why there won't be any charge? Suppose if it is a sphere, okay, if it is a positively charged sphere, so this will be radially outward, even here also radially outward. So here also radially outward, here also radially outward. So both will be cancel each other. So there won't be any charge inside. So when there is no charge, there won't be any electric field. So when Q is equal to 0, the total value will become 0. Okay, right. So now from these three situations of the shell, okay, we will come to know one conclusion, that the graph will show me how the electric field will be vary with the distance r. So up to the radius r, there won't be any electric field. Up to the radius r, there won't be any electric field. Okay, then when it reaches the point r, suddenly it is increasing the value. When I move away from the point, it will be decreasing. Okay, so E is inversely proportional to 1 by r square. Okay, so there is a conclusion we will come to know. Okay, now this is what the Gauss's law. So from the Gauss law, we will come to know the electric field, the electric flux, and also the areal vector. By using the Gauss's law, we have discussed the applications. What are the applications? Infinite charged wire, and plane sheet, and spherical shell. Thank you.